Okay, welcome. It's great to have someone show up to the webinar. And this is the week 10 webinar. We're almost done. And in fact, we only have up to the week 11 webinar because I don't give a webinar on the week 12 because some people are just completely done with the class by then. So next week will be our very last webinar of all. And this is the week 10 webinar. And I do want to remind you, this is week 10. What's important about the number 10, given that it's even?
An exam.
Yeah. So week 10 means exam week. So you will have an exam to do. And just a reminder, the exam will cover what we're talking about today and what happened last week. And it's has more of that, but it also has all the old stuff too. And hopefully you've noticed by now that since you've taken 4 exams already, that all the questions are randomized from past homework. Okay, except for the last few, and those are type in wording stuff. And at which it's really important that you pay attention to the webinar because I will let you know the words that have to happen for you to get full credit on the exam questions at the end. So that's just a note, and we've been doing that all along, but some people don't pay as much attention as they should. And I want to let you know that the that's also true for the discussion post assignments. Okay, so there will be discussion post assignment this week, and the wording that we talk about is important. So this is an exam week. I will always happy to answer questions. And then we're going to get into regression analysis. So regression analysis is actually one of the most important topics in statistics. It is used a lot. So we'll be doing that. And we talked a little already, but it was ages ago about scatter plots. But now we're really going to be focusing on the idea of scatter plots and seeing how they work. Then I know this looks easy. We're going to get R. So R is it, it's a letter that stands for something that is not the first letter of the word it stands for, but it's a letter that most of you have probably already heard before, which is correlation. So we're going to be looking at what is the correlation, and in particular, what is the linear correlation between two things. And that's what regression analysis is all about. Then we'll look at R squared, which, yes, is the square of R. It is the square of R, but it interpretation wise is more than just the square of R. It's going to have its own special interpretation that is very important and very helpful for all kinds of things. So we'll talk about R squared. We'll also talk about the equation of the regression line. So the if you have a scatter plot that has a high R squared, then it's going to kind of look linear. And you want to see what is the equation of that line that it kind of looks like. And we'll understand that. Here's something that you're not going to even, most of you will never do. And that is know how to do it by hand. So this is one of those, you got to trust me. There's a lot of math involved in coming up with this R and R squared and the equation of the regression line. We don't do the mathematics of coming up with the equation. Any guess on how you're going to find the equation?
Calculator?
Yeah, we're going to use a calculator. So this is a big calculator day, and it's important. And then I want to let you know that the word causation or cause is should pretty much never be used when talking about regression analysis. And in fact, it shouldn't be used in almost anything we do in statistics. And I have noticed that there have been people who even put cause in their H naught and H1 for hypothesis testing. And you shouldn't. All you do is you say the means are different, the means are the same, the proportions are different, the proportions are the same. You don't say this causes that. Okay. Instead, we're going to be looking at correlation only, and that's very different than causation. And I'll give some examples on that. So I'll let you know some of the words that you definitely need to avoid. And then finally, we want to say, is there a correlation between these things? And whenever you have a question of is there, then we're going to do a hypothesis test. And we're going to hypothesis test. It turns out the Greek letter for R is this looking thing, which is not a P, by the way. It's actually a Greek letter for R, not P. And it's said by rho, RHO actually, but or just this letter. And that's how you do it. And we're going to be looking to say, is there a correlation? And H naught will be there's no correlation, but H1 is yes, there's a correlation. So we'll talk about that, and then we'll talk about how you conduct the hypothesis test. And again, for this class, we are only going to be doing calculator work. We're not going to be doing any of the math to come up with these things. Okay, the only math, and there's some math today, and that is remembering about lines. And we'll talk about that as we go. So that is the plan today. I do want to remind you again, we're towards the end. Next week is very different. There are no assignments due next week. There is no webinar next week. Any guess on why?
Project 2.
No, nothing to do with the project, actually.
Oh, Thanksgiving.
Yep, it's Thanksgiving. Yeah, so next week, next week is Thanksgiving, and we're closed. There is no classes, there's nothing on. We get the whole week off. So I always like to say your homework for next week is to gain weight because you're supposed to eat a lot on Thanksgiving, right? Isn't that what it's all about? Okay, or at least part of it. So it's not to do statistics. So just to let you know, there's nothing due, at all next week. I mean, you do have this week's stuff. Sunday, you'll have a bunch of stuff due. Thursday, you'll have to do a discussion post. But next week is a free week. Okay. I mean, you're welcome to work on stuff, but nothing forced. So that's a big thing. After next week will be the last regular week where you actually do regular material, and that we call week 11. Next week doesn't count as a number. And then the week after that is the end. And that's just going to be your last exam, and that's it. So just let you know, light is at the end of the tunnel. We're getting really close. Okay. And again, except next week is a little weird in that there's nothing. So there are only this webinar and the webinar in 2 weeks. There won't be a webinar next week, and there's no webinar in final. So this is the second to last webinar. So are there any questions about anything? Any questions? Okay, if there's no questions, then we're going to get going. And since we have a very small group, we may need to change some of the things that I was looking at because this really won't work because can't do regression analysis on a sample size that is way too small. So I'm going to skip these and we need to do something else. Okay, we need to come up with and regression analysis is all about looking at two quantitative things and to see if there is a linear relationship between them. So, any thoughts on things we could look up possibly and see if there's a linear regression relationship? There's a lot of different things. Anything you're interested in? Because I can't really do a survey when we have too small a group. Any ideas? Okay, if you don't know, then maybe I'll ask you a survey question that's going to have a bunch of answers. Otherwise, this won't work. Okay, maybe 4 answers or something. So, and it'll be 2 survey questions. So how about, and I'll try not to make it too personal. How about, can you tell me, how about let's see if you can just guess. That's all you're going to be able to do. In the last 4 days, not counting today, so that would be Thursday, Friday, Saturday, Sunday, how many calories do you think you consumed for breakfast? And how many calories do you think you consumed for dinner? And if you don't know, guessing is okay. I'm going to allow that to happen. So we're going to look at that. How many calories did you consume for breakfast and for dinner in each of the last 4 days? Okay, oops, question mark. Okay, so let's go. First was Thursday. Not daily. No, these are very specific. On Thursday, think about what you had for breakfast and see if you can guess how many calories you had. How many for breakfast? If you don't know, make a guess. How many calories did you have for breakfast? Can't be less than zero. Any thoughts? Any memory? Okay, so Thursday, 500 for breakfast. And how many for dinner for Thursday? Okay, dinner Thursday, 850. Okay, then there was Friday. And that was 200 for breakfast. And dinner on Friday was 900. And Saturday, that was 700 for breakfast and 1,000 for dinner. And Sunday, the Sunday was 500 for breakfast and 1,500 for dinner. Okay. So what we have here is we have two survey questions. And the question is there a relationship? In other words, for example, on days at which you did not consume so many calories for breakfast, does that help you predict how many calories you might have had for dinner? So maybe if you had a lot for breakfast, you didn't need as much because you're not as hungry. You had a whole lunch and now you don't need much for dinner. Or maybe you just have days where you're just super hungry all day. And then if you have a lot for breakfast, then you have a lot for dinner. We don't know. Or maybe breakfast has nothing to do with dinner. Does that make sense? So that is the question. We want to see, is there a correlation between the amount of calories for breakfast and the amount of calories for dinner? Okay. And I just want to give you a big heads up warning. This is a sample size of 4. And in the real world, you never trust any sample sizes of 4 because you need big sample sizes. But, for this example, we'll do what we can. So the letter we use for correlation is called R. Okay. So that word is correlation, very important word. And you've heard the word, but you probably haven't heard all the mathematical details of it. A couple notes is R is always between -1 and 1. If R is -1, then that tells you that if you have a low first variable, so a low amount of calories for breakfast, then you will have a high amount of calories for dinner. And you can actually make an exact, perfectly linear prediction with a negative slope. Okay. On the other hand, if R is +1, then that means it's going to have a perfect linear prediction with a positive slope, which would mean more calories for breakfast, more calories for dinner. And you can actually come up with a formula for it. We'll get that in a little bit. Okay. If R is 0, that means there's no correlation at all. Okay. My favorite example, especially if you look up, although I think it's cloudy right now, but in the night sky and you look at the stars in the sky, do they look all lined up in one line? Or are they all over the place in the sky?
All over the place.
They're all over the place. The correlation between latitude and long, kind of forward, backward, left, right for stars will just be zero. Okay, or it's very close to zero because they're all over the place. Does that make sense? Okay, let's look at some examples and let's see if you can come up with some examples. Can you think of a real life example of two survey questions? Okay, or they could be measurements where R equals 1. Can you think of two survey questions? Okay, it wouldn't be how many calories you had for breakfast and how many for dinner, because you can't know exactly how many calories you can have for dinner if you knew how many you had for breakfast. Any thoughts on a real life example of two survey questions where the answer to the survey question is going to have a correlation of exactly 1, the highest correlation possible? Any thoughts? Okay, and the answer is a lot of them, but you have to be thinking the right way. Don't see you jumping in, so should I give you one or do you want more time? No, these are quantitative questions because you can't have a high number answer if it's yes, no question. Yeah, so with this chapter, there's no yes, no questions allowed. It's only quantitative, two quantitative survey questions. Because these are numbers. As one goes up, the other goes up. And if you have no idea, I can give a suggestion or I mean an example. Any ideas? Okay, rate your drive and amount of gas you use. So when you like rate on a scale of 1 to 10, how much or how far you drove? Like how far you drove? You say rate. Okay, so that actually is going to be very close to 1, but won't be exactly 1. And the reason for that is, for example, if I'm in Tahoe right now, if I drive to Sacramento, about 100 miles, and I look at my gas, okay, and then tomorrow I drive back home from Sacramento and I look at how much gas I used. It's not the same amount of gas. Coming down to Sacramento uses very little gas. Coming up uses a lot, even though it's the same amount of miles driven. Do you see? Okay, so maybe I'll give you one that actually does. So what if the first survey question was, how tall are you in inches? And the second survey question is, how tall are you in centimeters? Then that has an exact correlation of 1 because there is actually a mathematical formula that's a linear formula where if you know how many inches someone is, you can figure out how many centimeters they are. Does that make sense? Okay, so if there isn't some mathematical formula like that, then it's not going to happen. Okay, so that's the example I have. Others might be, oh, what is the temperature in Celsius? And what is the temperature in Fahrenheit? That'd be another one where there's a mathematical formula. So as one goes up, the other goes down. I mean, the other goes up also, and it's linear. Any questions on that? Okay, can you think of a real life example of two survey questions where R is very close to 0? Okay, and don't use my example. Any ideas? I'll think of a real life example of two survey questions such that R is very close to zero. If you type in a couple. How tall are you and your IQ level? That might be very close to zero. I've actually never researched that. I have no idea if tall people tend to be dumber or smarter. I really don't know. But if it's true that tall people are not smarter or dumber than short people, then that would be true. Okay. So that would definitely be true, but I actually don't know. Maybe you do, but I've never researched that one. Okay, but that's a possibility. Let me give you kind of a fun one I like is what is the temperature in South Lake Tahoe? And what was the total number of points in the soccer game in New Zealand at the high school in that, city in New Zealand? Okay, do you think the temperature in South Lake Tahoe has anything to do with the total number of points in a soccer game in New Zealand?
No.
Nothing at all. I can't imagine saying, "Oh, it's warm today in Tahoe, so therefore my favorite team in New Zealand is going to score a lot." Not going to happen. Okay, that would be ridiculously silly. Okay, so that would be an example. And it's basically when two things have nothing to do with each other, typically. And maybe the height and IQ might have close to zero also. Okay, come up with an example where the correlation R is close to -1. See if you can come up with one of those. So two measurements or two survey questions, something like that, where R is very close to -1. And there's a lot of examples, but they're a little harder to think about than one. Any ideas? So when would R be close to -1? Okay. Okay, so that's a good one. So let's think about is how much did it rain this week? And how many times this week did you water your flowers? Is that kind of what you're thinking about the survey question? Because if it rains a lot, then you don't need to water your flowers much. That's a great example. I think it's a really good example. Here's another example that's real is how many cigarettes a person smokes each day and how long they live. Okay. So people who, and hopefully you know this, because I think everyone's been taught this at this point, people who smoke a whole lot often have health issues, right? And die younger. Does that make sense? Okay. It doesn't mean that if you smoke a lot, you will die young, but you're more likely to die young. Do you see the difference? You have a tendency to die young if you smoke a lot. Okay. It's not a guarantee. And if you smoke, and if you don't smoke at all, like I never smoke, that doesn't mean I'm going to live a long life, but I have a better chance of living a long life than if I smoked a lot. Do you see how that works? Okay, so that's an example of R. Now R squared. Okay, so first thing, R squared is just the square of R in terms of the number. So it's very easy to find R squared if you know R. So for example, if r is 0.5, r squared will be 0.25 because 0.5 squared is 0.25. Okay. Do you think r squared could be negative? Yeah, r squared can never be negative because r is a number and a number squared is never negative. That's just a note. All right. And in terms of and this is just to let you know, this is the hardest part of the entire chapter is understanding r squared. So it's very important to get used to it. So first thing, it's better to think of r squared as a percent. Okay, so remember, if r is between -1 and 1, then r squared is between 0 and 1. So if r is, say, like 0.85, you want to think of it as 85%. So just let you know, it's easier to think about it if you turn that decimal into percent. And kind of the way it works is you want to think of the variation in the y variable is considered large. But if you just look at y values that all have x values that are almost the same, then on average, the variation, which is also called the standard deviation sometimes, is reduced by r squared percent. Okay, so that is the general idea of r squared. Okay, so for example, with the how much it rains versus how much you have to water your flowers, how much water you use on your flowers that week, what you can say is that there's kind of from week to week, there's a pretty large variation in the amount of water you use in watering your flowers. But if you only look at, say, weeks that have almost no rain at all, then that variation is decreased by almost 100%. Does that make sense? There'll be very little variation if you're only looking at weeks at which it all had the same exact amount of rain. Any questions on the idea of that? Okay, so now let's do the example. So we have these numbers, and I'm going to rewrite them just so I can type them in. 500, 200, 700, and 500 again. And then we had 850, comma, 900, comma, 1,000, comma, 1,500. Okay, and I want to find r, and I want to find r squared. I'm going to find other stuff too. Any guess on how I'm going to do that?
Calculator.
Yep, calculator. Okay. And again, I promised you that I was not going to even pretend to explain how the calculator works. But I'm hoping you know which calculator work to use. Which calculator should we use?
Number 24.
Yep, number 24, because this is the chapter on regression analysis. And I got some good news for you. Everything is in order at which we do things in this class. And guess what? After 24, all we have is 25. There's only one calculator left after this week, and we'll be done. Okay, that'll be Nova, by the way. But let's do 24, which is regression analysis. I click on that. Okay. And there's two choices. The easy way is to just put in the values of x separated by commas. And I copied and pasted. That's why I rewrote this with separated by commas. And then the value of y separated by commas. And it's very important that you keep them in the order at which they're written. Does that make sense? So this 500 corresponds or goes with this 850. That was Thursday. This 200 goes with 900. That was Friday. So don't mix them up. Okay. And then I just hit plot points. So we can see that in this case, there's 4 points. And here is the best fitting line to those 4 points. But when you look at these points, does it look like there's like without seeing that line that you would think that they were linear or even close to linear?
No.
Doesn't look like it at all. Okay. It does not look like those lines, the points fit anywhere close to a line. Do you agree? And that is told here. So R is about 0.20 rounded to two decimal places, right? And R squared is 0.04 rounded to two decimal places. So let's write that down. So again, R was 0.20. And it is important you know how to round things. And R squared, I'll write it as R squared. For some reason, they usually don't write R squared. They write R square. I don't know why, but that's what most people do. So I'm going to do what most people do. And R square was 0.04 approximately. Any questions so far?
No.
Okay, let's look at this R. The first thing, First thing R is positive. Okay, that should be obvious because it just is. There's no negative sign in front of it. So R is positive. So that means that of the correlation, as one goes up, the other tends to go up. Does that make sense? On the other hand, this positive R is like very small positive. It's not close to one at all. Do you agree? So since R is positive, but not close to one, closer to zero, right? We can say that there is a very weak correlation between the number of calories eaten for breakfast and the number of calories eaten for dinner. Any questions on that? Okay. So that's kind of interpreting the R. Let's interpret the R squared. R squared is 0.04. What we can say is that there is a pretty big variation in the number of calories eaten for dinner. But if we only look at days where the same number of calories are eaten for breakfast, that variation tends to go down, or on average, is decreased by 4%. By the way, is 4% a large percent or a small percent?
Small.
Yeah, it's tiny. So basically, it's meaningless if someone tells you how many calories they had for breakfast if you want to predict how many calories they had for dinner. Does that make sense?
Yes.
Because 4% drop in variation doesn't really change anything meaningful. Does that make sense?
Yeah.
Okay. Is that clear so far?
Yes.
Okay. So that's that's a good example. I do want to let you know this is a sample size of 4. So again, don't trust anything here because you should never trust a sample size of 4. Okay, but again, we only have so much time. Okay, so that was really important as an example. There's lots and lots of important examples. It comes up all over the place. Okay. So let's look at the most important example where I live. Okay. And the most important thing that happens in Tahoe in terms of actual measurements. Anyone know what that is?
Snow?
Snow's important, but not nearly as important as other thing. And is especially important for Tahoe and not important anywhere else. Almost no one else cares about it anywhere else. That's a
A
hint.
lake?
Huh?
A lake?
Yeah, and in particular, what about the lake?
Water levels or keeping it clean?
You clean, not levels, but clean. Yeah. Water level, hey, if it goes down 5 feet, no one really cares because our lake is so deep. You wouldn't even notice hardly. You'd notice, but not that much. But and in particular, what's called the lake clarity. Okay, so what happens, and actually UC Davis does this, and what they do is they measure the lake clarity every year. And what they do is they take a seki dish, which is basically a white plate, and they tie it to a rope and they slowly drop it down from a boat. They're in a boat in Tahoe until they can't see it, and then they stop dropping it down. And they measure how far that is, and that is how deep the lake clarity is. Does that make sense?
Yes.
And here's something that made me so happy. They actually came to our college once to it was an event, and they did some science stuff, and I got to talk to them about it. And I asked them, about how they did it, and how many days they actually measure the lake clarity, every year. And what they told me made me smile so much. You know how many? Can you guess? It would make me smile a lot.
Maybe every month?
No, not enough. Should I tell you? 31 days. Do you know why 31 days? Here's a hint. Think of Project One and Project Two.
For the sample size?
Yep. And they want to make sure it's like they took my class. They want to make sure they have a large enough sample size that they can assume that the average lake clarity for the year follows the normal distribution. Isn't that kind of cool?
That is pretty cool.
Yeah, I smiled so much. Okay, this is a lot of years ago they told me, but I'm sure they still do. Okay. And so that's what they do is they measure the lake many days out of the year because different days could have a different amount of clarity. They actually have to measure it on cloudy days because if it's a sunny day, it reflects and you can't see anything. So they measure on cloudy days. And this literally I pasted from their site. This is the average Seki dish lake clarity. And this was really neat. And this is something that happened in just at the around the year 2000. Okay, I've been teaching a long time, by the way. The president of the United States came to Tahoe, okay, along with some senators, our governor. It was like a main thing to talk about the environment. You may not even know who the president was then, but it was the year 2000. And I had a statistics student that was there. And they showed the president this picture. And the good news, unlike some other presidents we've had, is this president understood statistics and math really well, actually. It was actually President Clinton. And they actually talked to the president and the senators and the governor about the lake clarity and issues. And this is the chart they gave. If you look at this, does this look like there's like it's kind of not far from a line? Or does it look like it's all over the place, like the example that we had with breakfast and dinner calories? What do you think?
Looks closer to the line.
Yeah, if you look closer to the line, it's not perfectly on the line. So R is definitely not one. Here's a trick question. Is R going to be positive or negative? Is it going to be close to positive one or is it going to be close to negative one? Think of the slope of the line.
Positive?
Okay, what you didn't hear is the first few words I said. This is a trick question. It's negative. And this is a trick question. And I would never do this to you on a test or anything like this. But if you look at the y-axis, this is again, this was UC Davis. Here's 15 here, here's 20, here's 25. It's actually upside down. Do you see that?
Yeah, I see it now.
It's a trick question. Okay. It's actually, this is even though it doesn't look like a negatively sloped line, as soon as you realize it's upside down, it's a negatively sloped line. It's tricky. Okay. I didn't do this on purpose. This is them. And what I did is actually, I got the data and these are the years and they started collecting data in 1968. And before the president got here, they had finished in 1999. And so I just wrote down the years and I decided just to make it a little less typing. I didn't type in 1968, 1969, 1970. Does that make sense? And these are the meters that they were able to see when they dropped that, how far they can drop that Seki dish down until it disappeared in the water. Does that make sense?
Yes.
So we could do the same thing. And let's do that. And it might help to just refresh. Sometimes that's better. And pop the X values in and pop the Y values in. And I could hit new plot. Oh, sorry, I screwed up. Not new plot, I want plot points. One more try. Plot points. Okay, and here's the not trick question. Now it's obvious, hopefully, that the regression line has a negative slope. Do you see?
Yes.
Okay, and the sign of the slope is always the same as the sign of R, by the way. Again, the math is too hard to explain why, but you can trust me on that. Sound good? Okay, so there we go. We've got it. Now we can look at all these different things. Okay, this is very different than the other example. First thing, we got a big enough sample size. Is that clear? This isn't just 4 dots. Okay, second is we can now look at R, and R is about negative 0.85. Okay, so if R is negative 0.85 or so, that means we have a negative correlation. Do you see how that works? And
Yes.
now this number is pretty close to -1. It's a pretty strong negative correlation. Do you see that? Okay, so that means that as the years have increased, there's been a tendency for the clarity to decrease. Do you see that? Now, that doesn't mean that each year it goes down because there are some years, like between this year here, which might be like 1983 and 1984, when it went up. Do you see that? Do you see? For that one year, it went up.
Yeah.
Okay, but there's a tendency of downward. Does not mean it always goes down, but it's a tendency. Any questions on that?
No.
Okay, then there's r squared. And the idea here is r squared as a percent, rounded to the nearest whole number percent, would be 72%. So what we can say is there's a lot of variation in Lake Clarity in Lake Tahoe. But if you only look at kind of years that are all clustered close to each other, that variation decreases by 72% on average. That's a pretty big drop. Do you see that? Any
Yes.
questions on that?
No.
Okay, so the next thing we're going to do, this is very important, is let's conduct a hypothesis test. Okay, and the way the hypothesis test is if R is 0, and we're going to use, and R, by the way, it turns out to be a sample correlation. So if the population correlation, which is going to be used, you can use the Greek letter for that is rho. If rho is 0, that means there's no correlation at all, right? So our H naught is rho equals 0, no correlation. Got it? HA, and sometimes you call it H1, you choose, is there is a correlation. So rho is not 0. Do you see how that works? Any questions on that?
No.
So if we want to see, is there a correlation, which most of the time, that's what we're going to do. I put that as the first choice because that's almost always going to be the choices. Then the good news is this is always the H naught and H1. And you can call H1 or HI, you choose. Okay. It's always exactly the same for this chapter. Got it? And just to note, if you're doing this, for example, on the exam, for example, okay, or even on the discussion post assignment, and you can't figure out how to get this letter in, then you could type RHO equals 0. Does that make sense?
Yes.
Okay, so RHO is how you spell row. And I like to remember it is row, row, row your boat. Got it? Okay, so rho equals 0. And if you don't know how to type in the not equal to, type in NOT and then equal. Sound good? And I'll accept that for your tests and your, but you do need to have this here. Okay, you need to have H naught and H1. You need how to put it in, but I'll allow you to use RHO instead of the letter rho, and I'll allow you to use NOT with an equal sign instead of the not equal to symbol. Okay, if you're having any trouble trying to figure out how that works. Does that make sense?
Yes.
Okay. So we use that. It turns out, and again, the math is way too difficult for me to explain why. It actually uses the student's t distribution. Okay, and again, just trust me on that. Is the p-value, here's p-value, is the p-value around 9.67? Is that what the p-value is? Okay, the answer is no. Okay, remember, p stands for probability. Probability can never be 9.67. Can't have a 967% chance of something happening. Okay, and I want to really emphasize this because a lot of people make this mistake. What are you not looking at? In this box, what are you not seeing or not noticing if you thought the p-value was 9.67?
The E minus 10.
Yeah, what does that E minus 10 tell you?
The decimal goes out.
Yeah, to the left, it's going to be 0.0000000000967. Does that make sense?
Yes.
Which is as close to 0 as you can imagine for a p-value. So that means this is as strong statistically significant evidence that you could ever imagine having. Do you see that? And you can see just from the picture, you can visualize a line. Do you see that? There's no question. Do you agree?
Yes.
Okay, that doesn't mean every point is on a line, but there's no question that there's a line that kind of fits. Do you see how that works? So we have a very small p-value, and that means there is strong, strong, strong statistically significant evidence that as the years go by, the lake clarity has tended to decline. Do you see how that works? Okay. So there's a correlation between the years and the lake clarity. Any questions on that? Okay, and that's pretty terrible, right? My guess is since you're not that far from Tahoe, you know that we do not want our lake clarity to become really low. Do you agree? We don't want some cloudy, ugly lake. We want this beautiful blue Tahoe lake. Okay. So this is what happened actually. This was the year 2000. Okay, which I was here. I hadn't been here that long. I had been here. That was my like fourth or fifth year because I came in 96. Okay. And this was the year 2000. So around the fourth year or so that I was there, and the lake clarity is getting worse and worse and worse. Okay, so the next thing you want to look at is this line. So here's a line. And now comes a math question for you. If I ask you what is the equation of a line, there's two important numbers you need to think about. What are those important numbers when you want to talk about the equation of a line? You remember? You get this in middle school in math. Yeah, the slope and the y-intercept. Okay, so those are going to be the most important numbers in regression analysis. And especially it turns out the y-intercept. Not the y-intercept, the slope. Especially the slope will be important. So here we have it. Here's a regression equation, which is the equation of this line that is the best fit for those points. And again, the last thing I'm going to do is tell you how to find out how to get those numbers without using a calculator. Not going to happen in this class. So trust the calculator. Sound good? Okay, you probably don't need this many decimals. So that might be like, 45.6. And then plus negative means minus 0.25x or so. Does that make sense? Okay, so we want to talk about how do you interpret that. Any questions on that? Any questions? So let's go back because I put all this in here. Okay, so I want to remind you a little bit of math. The slope of a line is a rise over run. Do you remember that? Okay, the rise is a change in y, and the run is a change in x. And if you have a fraction, it turns out it's easiest, and you can always think of the fraction as having a 1 in the denominator, and the slope will be the numerator. Okay? And so we can think of x changing by 1 and y changing by the slope. So if x is increased by 1 unit, then y is predicted to or tends to increase by whatever the slope units are. Now, for our example, the slope was negative 0.25 about. Okay. And I'm going to write over 1. So the numerator is the change in y, which is the change in lake clarity. The denominator is the change in x, which is a change in years. So 1 means 1 year has passed. Negative 0.25 means the clarity has gone down by 0.25 meters. So the way we can interpret this is for every year that passes, on average, the lake clarity has tended to go down by 0.25 meters. And notice I turned that negative sign into the word down, which is usually what you want to do with negative signs, is you want to turn it into some word that tells you something has gone down, has decreased, has fallen, whatever it might be, has shrunk. There's lots of words for down. Any questions on interpreting the slope? Okay. Now a little bit of math. The y-intercept is the value of y when x equals 0. Do you remember that from math a long time ago? Okay. So now we need to take and try to understand this. If x equals 0 sometimes has no relevance or is far from the data values, or if the y-intercept has no relevance, then the y-intercept has no relevance. And that can happen. The slope will have relevance as long as our hypothesis test said there's a correlation. Okay? But sometimes the y-intercept doesn't have relevance. Otherwise, the y-intercept is the best prediction for y when x is 0. For our example, do you think the y-intercept has relevance or not? Okay, so let's look at this. Notice that if the data values, okay, if the y-intercept, if x equals 0 is far from the data values, okay, in this case, the x-intercept means x equals 0. Are there any x values anywhere close to 0? No, there aren't. Okay. Our data that we have is anywhere near 0. Okay. In this case, 0 would mean the year 1900. And we were not measuring lake clarity anywhere around the year 1900. So in this case, the y-intercept is again around 45.6. So if it had relevance, you would say our best prediction for lake clarity in the year 1900 is 45.6 meters. Okay, but none of the data is anywhere near 1900, so it's a terrible prediction. Any questions on that? Is that clear? All right. So here's the next question. What's the best prediction for the lake clarity in the year 2024? Which they're still measuring. We're almost done with 2024, but we're not done yet. How do we make a prediction? Any thoughts? Use the slope. Actually, a little more than use the slope. We use the regression line. I'm going to copy and paste the regression line into here. There's our regression line. I'm going to make it a little prettier by saying minus that. And the year 2024 corresponds to the number 24. I mean, the number 124. Because it's the years since 1900, right? And 2024 is 124 years after 1900. So there's our X value. And what we can do, I can pop this into the calculator. and it gives you 15 meters about. Any questions on that? Do you think we'd be okay? Do you think it'd be okay if our lake clarity went down to 15 meters from what it used to be? If you look at all the meters, what it was then, that's a big drop. Do you see that? Do you think that would be okay? Okay, so let me tell you what really happened. Okay. Again, this is just a prediction. This is a prediction based on the regression analysis. Okay. What this says is that if nothing changes, if we just keep letting things happen as they were, if they let things happen as they were going prior to the year 2000, then our best prediction for lake clarity would be only 15 meters, which is terrible. Okay. But here's what happened. When the president and the governor and the senators were there, they saw this, they understood statistics, which I told you I think is really important. Our politicians should understand statistics. They realized that would be a horrible disaster. So any guess on what they did? What can senators and the president do? Yeah, they passed a bill. Okay. For many, many, many millions of dollars, actually, to prevent this clarity damage from continuing. Okay. And there was a huge amount of money spent on trying to stop all the things that were causing Lake Tahoe to lose clarity. Does that make sense? Okay. And that happened basically in the year 2000. Because that happened, instead of the trend keep going up and up and up, that's not what happened. So here's a picture. And if you look from the year 2000, which is right here, to now, what do you notice about clarity? It went up, or actually, it kind of flattened out. Do you see that? Clarity got worse and worse and worse. They passed the bill, and then it flattened out. Does that mean it stayed constant every year? No, it didn't. Do you know why it didn't stay constant every year? Any guess? There's a reason. Okay. Weather. Turns out weather has a lot to do with clarity also. Okay. And if you get a whole lot of rain, clarity gets worse because mud goes into the lake. Do you see that? So it turns out that people are not the only reason why clarity can go up and down. Weather is also a reason. Does that make sense? So weather goes up and down, and again, changing weather. Unfortunately, we're changing weather, but we're not changing it in terms of what hurts Tahoe so much, actually, in terms of clarity. But weather's changing also, and so that's much harder to fix, by the way. So weather also goes up and down, and when it goes up and down, the clarity goes up and down, and that's why we're seeing the ups and downs, but we're not seeing consistent down in clarity. Do you see how that works? Okay, so let me mention a few things that are important. Okay, so we've talked about all this stuff. Here's some things that you should never use. Never use the word cause when you're talking about correlation. Okay, when you're talking about regression analysis. Here's an example. Okay, if you looked at people and you counted the number of gray hairs a person has and their age, do you think there'd be a correlation? What do you think? You say no? So you think people with a lot more gray hair don't tend to be older than people with no gray hair? Because that's what we're talking about. If you look at people that are, that don't have, that, are 15 years old, do you think they're just as likely to have gray hair? Okay, yeah. People with gray hair tend to be older. Do you know that? I hope you know that. Okay, that's no trick question. I think everyone knows that. Okay. Okay. And it's a tendency. Okay. That doesn't mean you can know their exact age by looking at their hair. Does that make sense? Okay. Does that mean that if I go in and dye my hair gray, that I'm going to suddenly get old? I'm going to cause myself to get suddenly old because I dyed my hair gray? What do you think? Or if I take a 15-year-old and dyed their hair gray, that means now they're 80? No, of course not. Okay. They would look older, but they wouldn't be older. I'm talking about being older, not looking older. Okay. So that's an example where there's a correlation between the two, but there's no causation. Having gray hair does not make you old. Do you see that? And it turns out there is a causation in the opposite direction. Getting older causes gray hair. Do you see that? So that's an example where you get a causation in one direction, but not the other. Is that clear? Okay. There are others where there's a strong correlation and there's no causation in either direction. Can you think of any like that? And that is usually when something else causes both things. Can you think of two things that are correlated when there's no causation at all, where one doesn't cause the other in either direction? Okay. All right. Let me give you an example. And this is an example that happened a few years ago. What was a big thing that was everybody was talking about 3 years ago? All anyone talked about 3 years ago, even 4 years ago. COVID. Okay. So what if you looked at people's temperature and looked at how much they were coughing? In the year 2020, was there a correlation between their temperature and how much you're coughing? There was. Okay. People who had higher temperature tended to be coughing a lot more. People who were coughing a lot more tended to have a higher temperature. How come? COVID. You get COVID, those are like two main symptoms of COVID. Maybe you don't remember, but those were the symptoms, those were the main symptoms of COVID. Do you remember that? Okay. Maybe you don't remember it, but those were the symptoms. Does that mean that if you cough a whole lot, you're going to have that's going to make you have a that's going to cause you to have a higher fever? Not at all. And vice versa. Having a higher fever is not going to cause you to cough. COVID was causing both. Do you see that? So do not ever say that because we have a strong correlation, that this causes that. I want to let you know, and this is something most people don't even think about, but what are the last 5 letters of the word because. It's not a trick question. What are the last 5 letters of the word because? Cause. So avoid the word because when you're talking about regression analysis. Got it? Because that actually does use that word because without even thinking about it. Okay. The other ones you want to avoid is avoid the phrase where if whatever you want to say, then it will happen. Does that make sense? Or it will go up or it will increase because that's another causation way of saying it. Instead, you want to use words like tends to increase. Okay. If one goes up, the other tends to also go up. Predicted to is another one. If one goes up, the other is predicted to go up or predicted to go down. Those are good words for regression analysis. Got it? If you use any of these words, you will lose points. That's a promise. Got it? Okay, so on the exam and on the discussion post, do not even think about using the word cause or because. Okay, and in statistics, you almost never can show causation. Okay. Turns out the only time you can is when you have kind of double blind control studies, which we talked about in week 1 of this class. But that's not regression analysis. Any questions on that? So correlation does not give you causation. All right. So this is what we talked about with light clarity. And this is the big thing that we talked about. Okay, let's do one more example before we finish. And let's suppose that we looked at the following. We looked at years of successful education after 10th grade and salary in thousands of dollars at 30 years old. Okay. And let's suppose this is the data we had. So this person had 6 years of education after 10th grade and made $75,000 when they were 30 years old. Got it? Kind of see how this works? The next person had 2 years, so maybe graduated high school and that's it, and only made $18,000. Do you see that? Okay. So we could do the same thing. You can take this data in. I'm going to go new plot. That erases everything. I can pop in the data. And then I can take this data in. And I'm going to pop this one in. And plot points. Okay. Often the first thing you do is you look at the hypothesis test. And we have H naught rho equals 0, HA rho not equal to 0. We have a p-value of 0.0001. So can we say there's a correlation between salary and age? I mean, salary and, number of years of education and salary. Can we say there's a correlation? Okay. The answer is yes. We have strong statistically significant evidence to say there's a correlation between number of years of education post 10th grade and salary at age 30. Is that clear? Okay, you can even see this line. Nice, strong fit line. Any questions on that so far? We have R equals 0.9. So we have a positive correlation. So as number of years of education goes up, there tends to be an increase in salary at age 30. Any questions on that? Notice the word tends to, not education causes your salary to go up. We can only say a tendency of when you use regression analysis. R squared is 0.82. So we can say that at age 30, there's a pretty large variation in salary. But if you look at all people who actually got the same amount of education after 10th grade, same number of years of education after 10th grade, then the variation in their salary on average tends to go down by 82%. Any questions on interpreting R and R squared? Okay. If we look at the slope is about, let's go, this is thousands of dollars. So how about 16? We'll round it to the nearest thousands of dollars. So we can say that for every year of education that a person has after 10th grade, their salary at age 30 tends to go up by $16,000. Okay, which is pretty much. Does not mean it is going to go up. It means that it tends to go up. Do you see that? Okay. How about this number, negative 27? Does that have relevance? That's the y-intercept. Is there relevance? Okay, so the first thing is we did have someone who had no education after 10th grade. They dropped out of high school. On the other hand, this is salary. Can you have a salary of negative $27,000? No, no. Jobs do not make you pay. That's not a job. Okay. There's fun things that make you pay, but not jobs, not salaried. So this would have no relevance because you can't have a negative $27,000 salary. So in this case, there is no relevance for the y-intercept. Okay. Had this number been positive 27,000, then you would say your best prediction for someone who dropped out of high school right after 10th grade is that at age 30, they would make whatever that salary is. But in this case, it's negative, so it's meaningless. Any questions on that? Any questions? Okay, so that tells us everything that we need about this example, at least for regression analysis. Is that clear? Okay, make sure you use the vocabulary that we're using for regression analysis. Okay, there's a lot of vocabulary I've been using. Look at this webinar, relook at it. I also use the vocabulary in the my discussion post. I always do a sample discussion post, and I use that vocabulary and make sure you use like the word tends to instead of causes. There's a lot of vocabulary that's important. Any questions? Okay, I do want to note something. Okay, so there's all the stuff we just talked about. Okay, if we want to make a prediction on one more thing, let's say we want to make a prediction on x equals 6, which means that 6 years after 10th grade, which is basically college degree, right? So you graduated high school and did 4 more years of college. That's typically a college degree. So if we plug in the number 6, you go negative 27.3391 plus 16.4084 times 6, you get 71. So what you'd say is our best prediction for someone with 6 years of successful education after 10th grade is that they will earn a salary of $71,000. Does that mean that someone who gets 6 years of education after 10th grade will earn a salary of 71,000? Does that mean that? Yeah, the answer is no. It's just a prediction. Okay, but it's a better prediction than any other prediction we could have. Does that make sense? Okay, so we've already talked about slope and y-intercept. I went kind of through those fast. I do want to mention one more important thing, especially when you're doing the regression analysis for the discussion post assignment. This is elementary statistics. That's the name of this class. Okay. That tells you something. One is there any more statistics after this class? Or have you learned everything there is to know about statistics by the time you're finished? Okay, no, of course there's more statistics. This is elementary statistics. So there's much deeper regression analysis than the regression analysis that we're doing. We're doing single variable linear regression analysis. I do want to let you know that there is multivariable regression analysis also, where you might have many variables and you want to make a prediction based on many variables. Does that make sense? We do not do that in this class. Okay, so do not even post a discussion post article that uses multiple regression analysis. That's when there's many variables. Only do one where it's a single variable regression analysis, where you have one variable in X, one variable in Y. Is that clear? Okay, let me tell you, even though we're not going to do this, but one of the biggest, I'm going to say this, see if you can guess. Okay, it's one of the biggest uses of multiple regression analysis, is one of the biggest things that's been in the news the last year or so that has nothing to do with politics, by the way, not about our president. Any thought? What's one of the big things in the news and they use that uses multiple regression analysis? Very complex. Any guess? Inflation has some, but that's not the biggest thing in the news in the last year and a half, actually. In fact, inflation hasn't really happened in the last few months. And when people talk about it, but it's not happening anymore. Should I tell you? Artificial intelligence. Isn't that big? That's a big deal right now. The way artificial intelligence happens is the back end of the computer looks at all the data, comes up with regression analysis, makes a prediction on what's the best way to say something, and then says it. Okay, and that's a big part of artificial intelligence. And again, we are not even thinking about doing the details of that in this class. But hopefully you can trust me on that because I do know that stuff. So AI uses a lot of regression analysis, but it uses multiple regression analysis. The other thing is sometimes there'll be regression analysis as nonlinear regression analysis. We don't do that either. Okay, and that'd be like instead of a line, you use a parabola or an exponential or something like that. We're not going to do that. We're doing linear regression analysis. Got it? So I figured I should give you a heads up in case you read something and it doesn't make any sense. So when you're posting your discussion post, your initial discussion post, make sure that you can answer it using linear regression analysis before you post it. Don't answer your own online, but make sure that it can be answered before you post it. That makes sense? Just want to give you that heads up because I'm just saying what a lot of people make mistakes on. So, since we're done, it's time for the secret word. And the secret word is because. Because I use the word because that is a word you should stay away from in your language and regression analysis. So that's a heads up. Don't use that word, but use it for the secret word. Got it? So the secret word is because, and it's a word that everyone knows. So hopefully you know the word because. Okay, so that is the end of the webinar. Thank you so much for coming. And of course, I'm always happy to answer questions. I'm going to turn off the recording. But thank you so much.